Yes. Before I start my Science for Peace credentials, my father was Irish, where my name comes from, and my mother was English. And when I was quite young, I found out that they'd been fighting for 700 or 800 years. So I decided to become a pacifist. Because I couldn't decide which side to fight on. Anyway, thorium is a different form of nuclear energy, different from what we've had in the last 60 years or so, which is based on uranium. Although actually thorium does turn into a kind of a different isotope of uranium. Now, how many of you, apart from Derek Paul, are physicists or chemists or one or two others? Okay. So the first little bit will be very boring for you, but other people might, actually if they come to all these lectures, they probably know it too. But anyway, nuclear energy comes about because the nucleus of atoms, in this case, absorbs a neutron, and the nucleus splits up into two or more smaller nuclei, and also gives off particles such as neutrons, which are the most important. Well, no, I wouldn't say the most important. It gives off neutrons, two or more neutrons, and other particles like alpha particles, which is a helium nucleus, and beta particles, electrons, and gamma rays, which are electromagnetic like light. And these particles, including the neutrons, carry a lot of energy, which is converted to heat, and that's used to turn water into steam and drive turbines. Now, when these two or more neutrons are given off, they go into another nucleus of the same or different element, and cause that one to split or fission, to split up. And on average, the design of a well-designed nuclear reactor, most of the time, on average, one of the neutrons resulting from one splitting or fission causes another one, so it just carries on, except at the early stages it has to be more than that. Of course, if there's more than one other one splits up, you get an explosion, either intentional or otherwise. Now, usually the neutrons are, okay, so the second nucleus is split, gives off more neutrons, they cause another one to split, and so on, in what we call a chain reaction. And usually, in most cases, the neutrons are slowed down or moderated because the slower neutrons are more likely to cause further fissions. And the moderators mostly used are water, regular or heavy water, or graphite. In many cases, graphite is highly undesirable. Some of the Russian reactors, up to the time of Chernobyl, including that one, use graphite moderators, and of course that's flammable at high temperatures. Although some of the thorium reactors use graphite also, which I'm not sure whether that's a good idea or not. Now, the elements or isotopes, I'll say what an isotope is in a minute. Oh, well, I'll say what that is first. An isotope of a given element, such as uranium, is the nucleus. The element may have several versions where the nucleus always has the same number of protons for a given element, but a different number of neutrons. And of course, nuclei are made up of neutrons and protons. If you want to know, ask me what neutrons and protons are, I just say they're made up of quarks. Don't ask me. Well, the different isotopes have different radioactivity rates. They decay at different rates, and roughly speaking, the more quickly they decay, the more powerful they are in terms of radioactivity. Some of them are stable. Eventually, they end up as stable. Now, the fissile isotopes that mostly are used or contemplated being used are uranium-235. That's rather rare isotope of uranium. Not terribly rare. It's 0.7% of the total. Plutonium-239, which is produced from uranium-238. Sorry if I have all these numbers. And uranium-233, which is produced from thorium, and that's what gets us into thorium. These are fissile in the sense they split off when they're hit by a neutron. Now, thorium is a little bit lighter than uranium. Uranium has 92 protons, and the most common one has 238. What do they call them? Neutrons and protons, anyway, altogether. Thorium is the second lightest natural element. It was discovered in 1828 by a Swedish chemist called Berzelius, and it became very important in the early days of research into radioactivity. It was had useful properties in that context. And the thing that makes it doesn't split itself. When it's hit by a neutron, it doesn't fission like uranium-235 or plutonium. But what it does is it absorbs a neutron, or sometimes two neutrons, and converts to uranium-233, which is does not occur naturally, as far as I know, but is fissile. It will split if it's put into a different part of the reactor, into the core of the reactor. Now, one of the advantages of thorium is it doesn't require any enrichment as uranium does. With most uranium reactors, they have to increase the amount of the U-235, which is the fissile one. By the way, if the chair will agree, I'd rather you ask questions as we go along. It would be less boring, is that okay? Rather than wait till the end, by which time we will have forgotten your questions.
Well, then let me ask one right away,
Yeah.
because I think you said thorium is the second lightest natural.
No,
could you
second
heaviest?
heaviest.
That's what I thought.
I
It
must have
be
said the
heaviest.
wrong thing.
Yeah. Okay. Thank you.
Well then,
Yes.
you say no enrichment is needed, and I guess recently, I'm just learning some of this stuff. To make plutonium, enrichment is needed of uranium, isn't it? And that's the really dangerous, aside from the other waste products, that's extremely dangerous for human beings.
Well, if you want to use uranium in a reactor, you have to enrich the U-235 to about 3%. But plutonium is a byproduct of the uranium reactor, and as we'll see later, that's one of the reasons that in the US especially they used it rather than thorium, because it produced plutonium, which they thought was a good idea in the Cold War.
But apparently that's extremely deadly
Plutonium,
for human beings,
plutonium,
aside from the weapons.
yeah, well, this is one of the advantages of thorium. It doesn't produce plutonium, or maybe very little. Plutonium is not, it lasts, its half-life is 24,000 years, so if you start with a kilogram, after that length of time, you have half a kilogram, and so on. Every 24,000 years it decays, so it's quite long-lived, if that's what you mean. I don't think it's as dangerous as many of the fission products, but that's the fission products like strontium-90 and cesium-137, iodine. They have much shorter half-lives, and therefore they're much more potent. Did I sort of answer your question?
Yes. I'm interested in human biological effects because
yes, of course, yeah. Anyway, the thorium doesn't need any enrichment. Well, it produces U-233 straight away, mostly U-233, which is fissile, can be used in, can be put back in the same reactor or a different reactor. Oh, and by the way, the enrichment that is needed can be done by various ways, centrifuges, gaseous diffusion. Centrifuges everybody's heard about in context of Iran. And I read recently that they had some that was 20%, which is not good enough for a good bomb. If it is very much in about 6 quotes at that side, an efficient bomb, but can make a sort of semi-efficient bomb. And then I heard that they had converted some of their 20% back to a lower percentage, which they thought would make people happy, but nothing makes the US and Israel happy. Maybe for good reason, I'm not sure about that. But that's nothing to do with thorium, really. The enrichment is expensive. And the advantage of, one of the advantages of thorium is not needed, it's not so cheaper. Now, some of the other advantages, it's much more abundant, 4 times more abundant than uranium, 3.5 to 4 times. The US and Australia has about 1 million tons, and the rest of the world altogether has about 2.6 million, according to Wikipedia. You can use 50% of the fuel compared to about 1% for uranium, unless in case of uranium you use expensive and dangerous breeders. Say more about breeders later. Because you can only use the U-235, and a little bit of the U-238 is converted to plutonium, which is fissile and can be used. Now the U-233 is produced from thorium. When the neutron bombards the thorium, it converts to another element, protoactinium, with a short half-life, and then to uranium-233, which, as far as I know, doesn't occur much in nature. And that, as I think I've said 2 or 3 times, can be reused in the same or other reactor. Now, another advantage is the spent fuel is safe, considered safe after about 800 years, compared to tens of thousands or maybe more years for uranium spent fuel. Although, if you reprocess, take the plutonium and other heavy metals out of the uranium spent fuel and use it in another reactor or in the same one, the waste disposal problem is much easier, because, as I said, the efficient products that are left when you take out the plutonium are quite short-lived. Yes?
I guess on the first page you mentioned Cantab.
Oh yeah.
Now the Cantab reactor can use natural uranium,
Yes.
unenriched,
That's
as
right.
fuel.
Yeah, I meant to say that. Yeah.
Okay. And then the other thing is that the thorium. Now, if you put thorium on the outside channels on a Cantab reactor, it would breed.
Yes.
And would you have to? You could reprocess that converted U-233
Yes.
to a fuel and feed it back in.
Absolutely, and in fact, the Indians are doing that, or planning to do that.
I guess the other thing is that you mentioned centrifuges and
Gaseous diffusion.
that's right. Now that's for uranium isotopes.
Yes.
The original process, when you recover uranium from ore, which contains both uranium and thorium, I believe it's a chemical separation, a chemical process.
Yeah. Yeah.
So if you made U-233 from thorium, you'd be using a chemical separation, which would be a lot cheaper than centrifuges.
Yes. That's sort of well, I hadn't thought of it exactly that.
It's just like refining.
That is the point. Yeah.
So it makes it a lot easier to reprocess.
Yeah.
Use thorium.
Yeah, if you have to separate different elements, it's much easier than isotopes of the same element. That's what you're saying, yeah. Absolutely. And as I said, the Indians are planning to make, they have, I think, a few already, but they're planning quite a lot of heavy water moderated thorium reactors. Yeah.
Excuse me, there's
yeah.
one thing I haven't understood yet. These thorium rods are going to be irradiated to become fissile, to acquire
Yes.
the U-233.
Yeah.
But can they then be put in the core of a reactor without a chemical processing in between, or must the U-233 be extracted and then put in a more concentrated?
From the thorium?
Yes.
Quite honestly, I don't know.
Because this would greatly facilitate the process if you
Yes.
didn't have to reprocess.
Yeah, you wouldn't have to reprocess.
Yeah.
I don't quite know the answer to that.
Okay.
Yeah,
Right.
sorry about that.
Yeah.
As I said at the beginning,
Yeah.
I'm not an expert, I'm just an amateur expert.
How would you reprocess it if you do? What, I don't understand the
Well,
process.
as this gen-
It's the same chemical, I would expect, it's the same chemical process. When you have ore, which contains uranium and thorium, they go through a refining process, which is chemical
Yeah.
separation of the uranium, and they throw away the thorium in the tails.
yeah,
You get the irradiated fuel and you just put it through the same, to my mind, you just put it through the same chemical process,
Yeah.
except this time, well, again, you're separating uranium and the thorium, and you can put that back in.
you would put it back into the bracket. Yeah, as far as I understand, you have a core of fissile material, mostly fissile material, and moderator, such as when you've got enough uranium-233, and that gives off neutrons, and you have a blanket outside which of thorium, which converts to U-233, and then you were asking, you have to reprocess it. No, it was you was asking that.
Chemically,
Yeah, chemically, but as you said, it would be relatively easy to do that.
The chemistry is there,
Yeah.
and the infrastructure is there. If you already reprocess the normal fuel, which for plutonium,
Yeah.
you're doing chemical processing in hot cells.
Mm.
So you've got the high radiation treatment equipment,
Yeah,
plus the chemistry, it should work easy.
yeah, yeah.
Everything's.
Well, this is not in my notes, but I just found out in the last couple of days, and I didn't have time to put it in the notes and so on, or the slides, but there have actually been, or in some cases still are, about 14 thorium reactors in the world have been constructed. Most of them have been abandoned for various reasons. They were too expensive or something. Some of them are quite big, about 300 megawatts, which is considered quite fairly big or intermediate level. There's a couple in India which are still working. I'm not sure, I did look at it, but just this afternoon, but I forget what kind they are. I think they might be heavy water, moderated, and thorium, and I think plutonium or U-235. They don't have enough U-233 yet to use it in the core. Another big advantage, if the fuel in a liquid salt thorium reactor, if the fuel overheats, there's a plug of frozen salt. Well, salt, when it occurs naturally, is frozen in the sense it's solid as opposed to liquid. Well, the frozen salt will melt at the sufficiently at the high temperatures, and the fuel falls into a container below and comes away from the moderator, which is probably graphite, or it could be other things like beryllium, lithium, I believe. Do you agree with that?
I don't want to think about the salt reactors, but if you're going to dump what's in there, you can put it into separate containers to
Yeah.
keep things away.
Well, it comes away from the moderator, and so the reaction is slowed down or stops. Yeah, so that's a very good advantage. You can't get a meltdown because it's already melted. And it's harder, not impossible, but harder to make bombs, which is for many people the most important advantage. And the reason is that the U-233 is contaminated by U-232, which has a very short half-life of about 70 years. And so it's very radioactive, and its daughter products, what it turns into, gives off, are even more radioactive. And according to Wikipedia, it's not in the notes, it was discovered a couple of days ago. But if you have more than 50 parts per million very small percentage of the contamination. You try to make a bomb out of it, it'll fizzle. And there was actually one test in the 50s, but in the US, the thorium, not the thorium, but U-233, it's hard to say, 233 bomb, but it fizzled. So I was glad to hear that. And the other reason is because it's radioactive, it's hard to handle to process the U-233. Question?
Yeah, if we just go back to if your fuel overheats.
Yeah.
So you think you're going to sort of stop the overheating by putting it into the salt where it's...
Well, it doesn't go into the salt. The salt melts and it goes through the hole into a container below.
Okay, now are these are waste products? And again, as I'm just curious about the effect on life.
Yeah, of course. Yeah.
Is it at all equivalent to the waste products of uranium?
Well, it will be in the short run, yeah.
Okay, so the short run is that the half-life is simply shorter than that of the uranium waste products.
I don't know the details of what, though I did look at it on the web, and there's a list of about 8 different products, fission products, and they have shorter half-lives. Well, the point is they don't include plutonium, which is very long-lived. Mm-hmm. And although, as I said earlier, even with plutonium, you could take it out and reuse it in another reactor, and then you don't have such a big problem of containing the waste. So yes, it's still a problem, but less than with uranium, much less than with uranium. Still a problem. You still need a waste depository, or whatever they call it. And by the way, as I was going to say in a minute, I describe myself as agnostic as between nuclear, in particular thorium, and wind. I think they're about the same safety level.
So what was the second thing?
Wind. Yeah, wind and nuclear. I did a lot of research on this about 2 years ago after Fukushima, and to everybody's surprise, wind has a certain amount of risk.
You mean the wind turbines?
Wind turbines, yeah. Wind energy, wind turbines. Yeah, blades can break and hit people. People can fall off the tower. In one case in Germany, a parachutist landed on the turbine, was killed. A woman in the early days. Now, well, I don't want to get too much into wind, but anyway, I'll talk a little bit about that later. So we mentioned how it's harder to make bombs.
Yeah, I'd just like to make one comment.
Yeah.
Because I've been asked this question with regard to thorium reactors recently.
Oh yeah.
The energy you get is, roughly speaking, not exactly, proportional to the number of nuclei that split. So for a given energy output with a uranium reactor, you get the same number of fission fragments within 10%, let's say, as you get with the same number of fissions in the thorium. So if you want to produce so many megawatt hours of power, you're going to have about the same number of fission fragments, and there's going to be a spectrum, a wide spectrum in the same general area of mass numbers of the fission fragments. That's the question that people didn't understand when somebody got on the news and said how much safer the thorium was. They thought that the waste problem had gone away. The plutonium problem goes away. The rest of the waste problem doesn't go away.
Yeah.
It remains about the same.
Yeah, and in either case, uranium with the plutonium removed, which they do in Europe and Japan and places like that, the waste problem is also not so bad.
Sorry, it's turned into what?
With uranium produced waste products, if you take out the plutonium, which they do in many countries, not in the US, it's illegal to do that in the US, because they're afraid of proliferation, maybe rightly, but anyway, a lot of countries do that. They take the plutonium out, reuse it, reprocess it, reuse it, and the the additional cost of doing that is about 1.2 mils, that's 0.12 of a cent per kilowatt hour, so it's very, very little.
Does Canada do that as well?
We don't do it as far as I know, but we could.
Don't take it out.
We could take it out, and then the waste problem would be much less. But anyway, with thorium, we don't even have to take the plutonium out, because it doesn't produce plutonium. Okay. Now, we were talking about wind. The book that I was, oh, by the way, I meant to say at the beginning, my talk is mostly based on the book Superfuel by Richard Martin, who was energy journalist. I don't think he was a nuclear physicist or anything, but he seems to know a lot about it. And I've also more recently consulted Wikipedia quite a lot. There's a very good article on thorium power, thorium energy, I think they call it, which is very much overlaps with the book. It might have been written by him, I'm not sure. But it covers perhaps a bigger area. Anyway, the book says that conventional nuclear costs 7.2 cents per kilowatt hour. And wind, according to the book, at that time cost 9.4, which is very precise. It's kind of a bit meaningless to be so precise, because different estimates vary a lot. And with wind, according to I think it was Wikipedia, one of those websites, there's a big project in Quebec being on the way, 2,000 megawatts, and it's estimated to cost 10.5 cents per kilowatt hour. Kilowatt hour is the thing you pay for in your hydro bill. Average house is about I think it's 3 kilowatt hours a day. It doesn't sound very much. Would that sound about right?
It's like ballpark.
Pardon?
I say it's the right ballpark.
Yeah.
I think a lot of people use more, but
Oh yeah.
yeah.
But excuse me,
Yeah.
if wind is coming down to about, just 3 cents a kilowatt hour more than conventional nuclear, I mean, isn't that,
Well,
they're almost on a par?
well, you're partly right. Wind, the project in Quebec is going to cost 10.5 cents per kilowatt hour, and some of the other estimates on the website are like 5.5 cents, so cheaper than nuclear.
Mhm.
But you also have to store wind power, the energy produced.
Yes.
And conventionally, that costs about 4.5 cents. But I did read an article in one of the engineering journals about a year or so ago, pointing out that you could build a big hole in the ground. I don't know if you build holes, dig up a big hole in the ground, put water in it, a certain amount of water, pump it up and down as you down when you need the power, and up when you have surplus, say at night, or when the wind's not blowing, or when the sun's not shining. And he estimated it cost about 1 cent per kilowatt hour. So, but no one's done this. So, no one's done thorium, so I don't know what it costs. Oh, that's not quite true. They have done it. Solar, I think that's a mistake. The 33, I kind of revised that this afternoon. It should be more like 23 cents per kilowatt hour. So, it's more expensive than wind.
Sorry, that's photovoltaic.
Well, actually, this was based, no, I think that would be more. This was based on a big plant in Texas that was being considered in 2009. And they estimated it would cost $6 billion per gigawatt. And that works out, I think, at about 23 cents a kilowatt hour.
For solar thermal or solar photovoltaic?
It's solar thermal. It's
Thermal.
not photovoltaic, it's thermal. I think what it is, the book didn't go into details, but I know that if you have a big parabolic mirror and concentrate the sun on a boiling water or lead or something like that, and drive a turbine, that's more efficient than photovoltaic. On the other hand, with privately owned wind or solar, you get away from all these hydro, what do you call them, overhead
Fixed
costs.
charges.
Sunk costs.
Hmm?
Sunk costs.
Well, things like delivery cost. Where I live, it's $70 a month. It depends partly on how much you use. It used to be a flat rate, but they changed that. And you know, the debt retirement cost and other odds and ends, like
By
things like that.
delivery cost, you mean just the cost of putting the wires?
Well, it's the amortization cost of the wires and stuff like that, I
Mhm.
suppose, and anything else, transformers and so on.
I have a country property and half the charges are connected with delivery.
Yes.
So I'm actually paying 29, if you take my whole bill and divide by the number of kilowatt hours, it's 29 cents a kilowatt hour.
Altogether.
It's what I'm paying
Yes.
in Northumberland
Including
County.
all the odds and ends.
Yes.
Yeah, well, that's what I was going to say at the end of the talk, but we're jumping around, and that's fine, because even if you have central wind or, you know, like big turbines, a whole turbine farm with hundreds of turbines up near Lake Huron. Funnily enough, near the Bruce nuclear station, there's hundreds of thousands of big wind turbines. Probably because they have the right transmission lines and things. It's near the lake. But like you said, 29 cents kilowatt hour. So even if your wind costs 15, it would only increase the cost by, I'm just thinking aloud, 15 as compared to 7.5, over 29, what's that? About 2.5, about 25% more, but not 3 times more as in solar or 2 times more. It's less more.
Do they include the capital cost?
Pardon?
Those calculations, do they include the capital cost? The
Which-
cost of building the, say,
The capital cost.
yeah.
Oh yeah, it's mostly, I mean, in all of these things, it's mostly capital cost.
I'm surprised that nuclear would cost less, considering how expensive it is.
Well, that's, I've seen other estimates, and 7 or 8 cents per kilowatt hour. You see, once you built it, it costs very little to run. The fuel is very, very cheap at the present. Oh, another question, yeah.
Right now, the cost of decommissioning in the UK is going up astronomically. The decommissioning costs and the costs for dealing with waste are never counted in the price of this kind of power for nuclear. And the stranded debt you pay on your hydro is the result of the original construction costing far more than they budgeted. 2 to 3 times more.
Yeah.
So it's a bargain only because the state decided to subsidize it. If it were a level playing field and those building it had to pay all the costs, it would be a different story altogether.
Yeah. Well,
And without the safety risks that wind and solar don't comprise the
well,
safety risks.
actually, there are risks with wind and solar, which there's a risk of a large number of small accidents compared with nuclear, small number of large accidents. We've had 2 large accidents, well, really, we've had two large accidents in the last 60 years. Wind is, you know, the amount of wind we've had has been very small, and there's been a certain number of accidents. And if you prorate that to producing all your power from wind, you would have a lot of
But the
deaths.
consequences of wind accidents are nothing like those of nuclear. And the reason that nuclear accidents are inevitable is because we, as human beings, are not infallible. It was institutional failure that caused Fukushima Daiichi reactors. So.
Yeah, we have and will get large accidents with nuclear,
Yeah.
and we'll get a lot of small accidents with wind and solar. and they balance out. I did a lot of research on that a couple of years ago, and they're about the same with certain. It's very surprising result. I was surprised myself. But anyway, I'm not here to advocate for nuclear in general. I'm just trying to show that thorium is better than uranium, according to various sources. Now, thorium probably costs less than conventional nuclear because you don't have to, enrich the fuel, and the disposal problem is less, and so on. Now, because of the advantages, several countries, especially India and China, are planning thorium power projects. Later we could talk more about the safety aspects of nuclear in general. I won't say much about the disadvantages of uranium because that's just the mirror image of the advantages of thorium. Except something that I put in recently, I discovered that the uranium-plutonium breeders, they use uranium-235 in the core, U-238 in the blanket, and breed plutonium, which can be reused. That needs fast neutrons, which is not a problem, but it needs sodium coolant up to now. It's used sodium coolant, which has often been led to accidents because sodium, as you know, explodes on contact with water. You have to have water to drive the turbines, to convert steam and drive the turbines. But I found out lately that the Russians are working on molten lead cooled breeders, which are probably much safer. And
What breeders?
molten lead instead of sodium as a coolant. I'm not quite sure why they have to use sodium or lead as coolants in fast breeders, but something to do with the moderation or something. I'm not quite sure. I used to know 30 years ago. I was very keen on breeders then, but now I'm keen on thorium.
The sodium neutron capture cross sections are not too horribly high, and the lead will be even lower.
Oh,
you have a minimum. Lead is a closed shell nucleus, and so the neutron capture cross section will be low.
yeah.
So there'll be very few neutrons lost in the lead, and the lead won't get as radioactive as any of those other elements. Sodium, for example, would get radioactive. It gets very radioactive in the cooling channels.
The sodium does.
Oh, very, very. Sodium 24 is very radioactive.
Yeah.
And it's a problem.
Well, you said lead is closed.
It's a closed shell nucleus. It's a very low cross section for neutron.
And that ties in with the fact that most radioactive materials end up as lead, don't they? I mean, uranium, blah blah blah, goes down to lead, and thorium does too, I think. Anyway, so much for disadvantages of uranium. Now we talk about the how's the tide going? In the early days of nuclear, there was quite an interest in thorium, and Alvin Weinberg in Oak Ridge mostly, he supported thorium because he thought it was safer and cheaper and also perhaps more abundant, although in those days we didn't know much about how abundant these various elements were. But Admiral Rickover, who was high up in the US Navy, he favored uranium reactors. Now, he was making nuclear submarines as fast as he could, as soon as he could get funding from the Congress. And I think perhaps, I'm not quite sure, but the uranium reactors were smaller than the thorium ones. They fitted better into a submarine. And actually the US used a German designed submarine, like they used the same shape. And it was a certain size, and the uranium reactor just fitted nicely. And a lot of people suspect that they also favored it because it produced plutonium for bombs. I mentioned, I've already mentioned that. But because this was all going on during the height of the Cold War, the US on the whole went into nuclear research and development. Not just nuclear, but nuclear research and development went into plutonium producing uranium reactors. Well, very early on, Weinberg 46 designed a water-moderated thorium breeder, which the Indians, which the sort of thing the Indians are using a lot, or planning to. But the pressurized water reactor and also the boiling water reactor, they won out because they were good for navies, as I just said, and good for making bombs.
I hate to ask a dumb question, but
Yeah.
I don't know what a breeder reactor is. A breeder.
Oh, yeah.
It's a term
okay.
that I just.
A breeder.
if I could-
Well, a breeder reactor is one. Yes, I should have explained that. It's a good question. Breeder reactor produces more fissile fuel, which can split off and produce a chain reaction. Produces more than it uses. You breed, like when you breed animals, you end up with more animals, and especially rabbits, than you started with. So it's the same idea. You end up with more you started with, and to do that with uranium, you have to not moderate the neutrons. You have to let the neutrons go at full speed as fast as they want. And then, for some reason which I don't understand, it seems like a paradox. If they're fast and they go into, say, uranium-238, which is not fissile, can't split, it produces plutonium. And maybe you understand that. Why is the absorption cross-section bigger for fast neutrons? Intuitively, you think they go straight through. Well, anyway, I'm glad that somebody else doesn't understand it like that. Maybe we'll think of it later. Anyway, that seems to be the case. If they're fast, they're more likely to be absorbed and convert the fertile material, which could be thorium, into, well, actually with thorium you don't need to be fast, you can be slow, you can slow them down, moderate the neutrons, and they will still breed. And that's why you can use nearly all the thorium, at least 50% they say. Now, this is really nothing to do with, well, it is to do with thorium. Most of the thorium designs do not use water, they use liquid fluorides, thorium fluoride and so on. But most of the accidents have been because of exploding steam. Apparently that's what happened at Chernobyl. So that is one of the advantages of thorium. It won't cause that kind of accident because it doesn't use water. Well, not as a moderator, but there'll be water eventually to produce steam for the turbines. That'll be in the outer layers of the plant. Something the book mentioned, which I was most surprised to find out, that in 1940, very early on, in Cambridge in the UK, they designed a tiny, I think it was a football-sized, heavy water uranium reactor, kind of powdered uranium mixed up in heavy water, which is what the Cantab uses. Heavy water is, has hydrogen, which contains proton and neutron instead of just a proton. So it's heavier than ordinary regular hydrogen. But that's just an aside. It's got nothing to do with anything really, just a point of interest. And then I think maybe I mentioned that Weinberg he had an idea of a reactor using a slurry of thorium and U-233, but that wasn't built. And then the US attempted to design a nuclear-powered aircraft, presumably a bomber, and that was fruitless in that respect. It never got off the ground. I think actually one did actually get off the ground for a few miles, rather like the Wright brothers. But it did. They are working on a design for a molten salt breeder reactor, that is one that produces more uranium-233 than it uses, or whatever else it uses. And that went, and Weinberg took this up and designed one, and his reactor went critical in '65. And a few years later, it started off with entirely to the uranium, but I think it had thorium on the outside, I'm not sure, in the blanket. Anyway, it had 235 in the middle, uranium-235, and that was replaced by uranium-233 from the thorium that had been in the outer blanket. And then he planned a larger demonstration reactor. That, I believe, was only 7.5 megawatts, it's very small. And of course, he planned a bigger one, but that was turned down because the reasons that we've talked about several times. The powers that be favored the liquid water reactor based on uranium. In spite of the fact that Weinberg's reactor ran at 85% of power for 15 months, which the book I'm referring to considers a remarkable achievement, but it was abandoned, as I said. Now, the head of the Atomic Energy Commission in the US wasn't interested in thorium because he wanted to spend his money on the uranium-235 plutonium breeder, which as I said will produce more plutonium than it uses U-235, using fast neutrons and sodium coolant. But that was never built either because they had too many problems or because they got worried after 3 Mile Island. Seems to be different reasons, or both. Although the French had a very big breeder reactor, the Super Phoenix, about that time that worked very well, but it was abandoned for political reasons.
It also was abandoned because 3 of the 4 cooling channels ceased to work. They had parallel 2 cooling channels, and the second, third, and fourth being safety, so in case one got blocked. Well, one did, and so they operated for a while on 3, and then one more got blocked, and they were operating on 2, and when that failed, they closed it down. But it was political, obviously, because they could have gone, they could have fixed it. Yeah.
They could have fixed it, yeah. Yeah, there's always problems which usually didn't fix, but sometimes not. Okay, well, anyway, as I said, thorium was not popular with the powers that be, and in 1973 Weinberg was fired. And the uranium-238 plutonium breeder, the fast breeder, sodium cooled, was funded, but as I think I said, it was cancelled after 3 Mile Island. Now, this is nothing to do with thorium really, but Rickover, who was the great proponent of nuclear submarines and built, I don't know how many, anybody know how many, 50 or so I think. We had them in Scotland, ironically, in the, what's it called, the Holy Loch in Scotland. I went up there, sat down outside, but just before I came to Canada, it was one of his submarines, and they had Polaris missiles and so on. Anyway, he was interviewed by Carter, what's his name, who, oddly enough, was a nuclear engineer himself originally. And Rickover spoke to him and greatly regretted his role in the arms race, the nuclear arms race. Although he was still making nuclear submarines, he didn't stop, he just felt bad about it and carried on. On the other hand, Weinberg believed, just before he died in 2006, he must have, I think he was well over 90 when he died, he said that he believed that mankind would overcome the problems and go into the second nuclear era. I'm kind of paraphrasing what he said about potential in the notes, and by which he meant thorium. And by that time, throughout the world, a lot of interest in thorium had being revived. And then in the 21st century, to some extent in the late 20th, the one particular person, Kirk Sorensen, was one of the leaders of the thorium revival. Nothing has been done yet, but there's a lot of plans and agitation and so on. He realized that the early work on the thorium reactors in the 1960s had been done at Oak Ridge. And he wasn't originally a nuclear engineer, but he got interested in it. He was some other kind of engineer, I'm not sure. And he had the Oak Ridge archives, which were concerned with the thorium reactors and so on, had them digitized in the early 2000s to make it easier to read the archives and read the plans for the thorium reactors. And then he became a student of nuclear engineering at Tennessee University. And his professors said, oh, he was keen on thorium. He mentioned it to his professors, and they said, well, if it was so good, it would have been done a long time ago. But a lot of people think there were more sinister reasons than that, namely, the thing that we mentioned 6 times, that the other thing produced plutonium for bombs. And he calculated that 1,500 tons of thorium would power the world for 1 year. That was kind of a homework project he did. And that means that since there's 2.6 million tons, that would work out at about 1,400 years, I think, 13 or 1,400 years. And then John Kutch, who was already a bigwig, was working high up in some big nuclear company, but he set up the Thorium Energy Alliance, which is purpose is to lobby the politicians and the financial industry for aid in developing thorium energy. And they have conferences every year for the last 5 years or so, and I'm going to one in Chicago in May. If anybody's interested, I can give you a reference. By the way, oh no, it's all right. I was going to say, if anybody, we don't have 15, I made 15 copies of the paper, and there's considerably less than 15
There's
here.
some here.
Yeah, you've all got copies, or could have copies. Now, there's many projects underway. I just found out this afternoon there's a big project going on in Norway with thorium, and several other countries, especially India and China, in that order. Before we go back to India and China, some of the recent trends in design for small mass-produced reactors. None of them have been built, but there's a lot of designs. And there's an international committee that's looking into these designs.
I'm sorry, what do you mean, small mass?
More mass-produced. Instead of building one at a time, and up to now, roughly speaking, each one that you've built had to be redesigned. You always try to improve them, and
So it's like a car assembly line or
yeah,
something?
yeah, assembly line. It wouldn't produce as many as cars, but you might produce a few hundred, I suppose, smaller ones, and they can be transported to the site where you want to use them and produce electricity. Now, something that doesn't really belong here, but is interesting, another advantage of thorium or the liquid fuel cores, the removal of xenon-135 is much easier from a liquid than from a solid. And I tried to find out this morning, I mean, looking at the web a lot in the last few days, getting ready for this, I couldn't find out how they get it out of the solid fuel. Do you know, Paul? Because xenon-135, it's xenon is a noble gas, it's a gas, but it's a big neutron absorber.
Yes.
So they have to get it out every 18 months, I think. They probably have to reprocess the whole thing, or just abandon it. Yeah.
But that's the long-lived xenon, right?
Yeah.
With the Cantab system, they have continuous refueling.
Yeah.
So when the spent fuel goes out, it's not in the reactor anymore.
Oh, okay, so they abandon it, as I said. Yeah, they don't try to
Yeah, with
reprocess it.
Scandu, there's no reprocessing of fuel, it's just
No.
once through.
So,
And they can each fuel channel is independent, so
yeah.
once in the center, they send
Yeah. So what this means in the case of the liquid fuel thorium reactors is that you don't have to abandon the fuel. You could just keep it going for, let's say, up to 30 years without recycling it. I'm not sure of that, but I think that I've read that. Because that's one of the reasons that the xenon will just come out much more easily.
But you have to get the fission fragments out from time to time.
Yeah, I suppose so, yeah. Yeah, you might have to recycle it in some sense.
Well, I read somewhere that on the liquid fuel reactor they'll float.
Oh, yeah.
So it's possible to remove them physically, like
Oh, that would be
spooning them
terrific.
off the top.
Yeah, that would be great, yeah, to spoon them off
Yeah,
with a remote spoon.
hopefully.
Okay, good. I think we've mentioned it several times before that well, any kind of thorium reactor can breed in the sense of producing more U-233. I've said that before. A lot of things I'm repeating, partly because the book, I got all this by going through the book twice and making notes and abbreviating it, and he jumps around quite a lot and repeats himself, so I did that. Next time I give this talk, I'll probably cut out some of the repetitions, and in some ways it's not bad because repetition is the key to learning.
Exactly, redundancy is to be welcomed.
Yeah, okay. Now, India, as I said, there's several, the book was published in mid-2012, it's quite new. There are one or two other books, but I haven't seen them yet. Several thorium programs planned, and now India in particular plans a large number of heavy water moderated thorium reactors. And now the author of the book is very skeptical about the Indian program because he says they have a lot of technical problems now. For example, they have, I think they have 20 reactors at present, but on average they work at 7% capacity, or have done over the last many years. So they have 20 reactors which are rated at many gigawatts, and they only produce about 500 megawatts, enough to light up Guelph or something. Anyway, they're planning a big development. There's 3 stages. First of all, the conventional pressurized water reactors will produce plutonium from uranium, as they do all over the world now. They'll put the plutonium in a fast breeder, which we've talked about, sodium cooled, I suppose, and that'll produce uranium-233 from thorium, as we've mentioned many times. Also plutonium from U-238, and that's probably for sinister reasons. They want to make more bombs, I suppose. They're one of the few countries that hasn't signed the non-proliferation, if I'm not mistaken. Proliferation Act. And then the third stage, oh, by the way, the second stage, the plutonium in the fast breeders, they've got under construction 500 megawatt, which is fairly big example of that under construction. And then after that, they've got more plutonium produced, and then they'll use heavy water moderated thorium reactors and U-233 in the core. And this will be Cantab types, as far as I can make out.
You're talking about India still?
India. I'm talking about India, but I think they built some Cantabs a long time ago, and they were cut off from world health until quite recently, as you probably know, because of their bomb-making plans and actual tests and things. But lately they've been put back into favor.
But
Yeah.
from a previous lecture, wasn't it stated that Canada itself sold India some
Yes.
of these?
They sold the Cantabs, yeah.
Yeah.
I believe so, yeah. Yeah, I'm sure they did. And then after they let off their bomb tests, the Canadians wouldn't collaborate with them anymore until fairly recently. I'm not sure if they are now, actually, or not. The US is, though. Anyway, the idea is that they have a lot of these heavy water thorium reactors, and they should produce most of India's power needs. Again, and they said, their experts say that the world will run out of uranium by mid-century. Western experts scoff at this, but personally I think that if a lot of countries like India and China were to use more and more uranium reactors, we would probably run out by. The current idea is about 100 years, but if we expand our uranium programs, then 50 years would be, well, it's less than 50 years, it's 40 years now.
Do you have a comment on that?
Pardon?
The short-term thinking of human species, do you have a comment on that?
There's a lot of noise outside.
There is, I'm
Yeah.
sorry, we can't.
Short-term thinking.
Yeah, well, I'm interested in human biology, so I'm interested in the effect. And human beings are, as a species, quite short-term thinking.
Oh, short-term
They think
thinking, yeah.
now, and in one generation.
Yeah.
And 40 years is about a little less than 2 generations.
Yeah.
And so I just ask, what's your response to?
Well, this is why the Indians are planning thorium, to use thorium, which will last for 1400 years, by which time
Oh, well, we'll have some
maybe we'll
excitement.
have controlled fusion work. Now,
In
this
1400
is about
years it might
We're also
happen.
very
shaking your
optimistic.
head, and I know. The critics say fusion is always going to work in 50 years, and that's been the case for the last 60 years or so.
Yeah, so we have a few generations.
Well, fusion will not be cheap if it ever works. But anyway,
It will not be cheap, and if it ever works, in the early phases, it will be fueled by tritium from nuclear reactors.
yes.
So it requires, as it operates now, or as it is, they're trying to make it operate now, it uses tritium as a fuel. And the only kind of device that produces a lot of tritium is the CANDU.
Yeah.
So you need, in my estimation, 5 CANDU reactors operating to keep 1 fusion reactor going.
Yeah.
And so the concept that fusion will replace nuclear power has to be established, because it's, at the moment, it's still a fiction. I'm not saying it couldn't happen.
Yeah.
I'm saying it's a fiction at the moment.
Well, they'd have to get it working with deuterium, wouldn't they? And if they could get it working with deuterium, which probably need a much higher temperature.
It does, yes.
And there's a lot of deuterium in the oceans.
Yes.
Yeah. Anyway, I mentioned some of these points, and I think I mentioned particularly their fast breeder reactor has been plagued by problems, so the author is skeptical about that. China is much more likely to succeed in the estimation of Richard Martin, anyway, probably right. A couple of years ago, China started work on a thorium molten salt reactor in collaboration with ACL, as it then was. It's now been, ACL has been sold to another company, as you know, but apparently they're still collaborating. They have at present 15 reactors, which I believe really work. They're building 29 more and planning even more. And they're hoping to have 2 molten salt reactors working by 2015. That sounds like very fast. But anyway, they probably don't go through, what's these things, environmental reviews in China. Maybe they should.
Ethical reviews.
Pardon?
Ethical reviews, they don't have to go through all
No. Now, there's quite a few private programs going back a bit in time, quite a lot. Shippingport Atomic Power Plant, or whatever it's called, went critical in 1957. It was one of the first commercial reactors, at least in the States. And from 1977 to 1982, it ran on uranium and thorium. And it was found that it produced more fuel than was used, so it was a breeder in that sense. Now, a bit later, the chief designer was Reactor, I presume he was Jewish. He went to Tel Aviv, and a bit later, no, he went to Tel Aviv in the early 80s, I think, I'm not sure when. And in 1983, I think after Shippingport was closed down in 82, he went there. And soon after that, Edward Teller, who you've probably heard of as the infamous father of the H-bomb, he urged him to restart his work on thorium reactors to reduce the chance of proliferation. It's very interesting. Most people in this room would probably regard Edward Teller as a very bad person, but he was a very good scientist, not in the moral sense, but in the sense of being a very smart scientist. He was one of the co-discoverers of fusion in the sun and stars, if I'm not mistaken. So he probably knew what he was talking about. So the fact that he thinks thorium cannot be used to make bombs is very much in favor of that being true. Anyway, that Reactor set up a company, I forget the name of it, Thorium Power Company, I think, to make solid fuel reactors, thorium reactors. And 2009, he tested fuel rods in his experimental reactor successfully. And solid core thorium reactors are much less prone to meltdown than uranium ones, because the melting point of thorium is about 500 degrees Celsius higher than uranium. And then, well, I mentioned all that, except thorium reactors can burn plutonium from bombs. They can use it up and make it no longer, well, turn it into fission products, which are much shorter lived. 1,000 years or so compared to maybe hundreds of thousands. So can uranium reactors, and that has been done in the States using plutonium from dismantled bombs from the USSR, and also from the States itself in the late 90s and early part of this century. That was done. I think they use it all up now, and the price of uranium is going up again.
Now, this is something to celebrate.
To celebrate,
Yeah,
absolutely, yeah.
You use the thorium to get rid of your plutonium.
Yes, well, you can do it with uranium reactors too. You can even use it in a breeder and make more plutonium.
Great.
Which, as long as you use it in a power reactor, is a good thing. Anyway, that we come to almost the last slide.
Oh, can I ask a question?
Yes, of course.
To follow through that, as some countries are trying to get rid of their bombs,
Yeah.
their weapons, is this a potential way then, instead of storing it in the ground and
Oh yeah, it's a much
building
better
things?
way, yeah.
It's almost like alchemy, isn't it? It's recycling.
It's exactly alchemy, transmutation, yeah.
So
Yeah.
recycling the bad back to a potentially less bad
Yeah,
thing. We
Yeah.
can do that.
yeah.
Wow, I didn't know that.
Can you,
I think one of the Fukushima reactors was using MOX fuel.
which is what?
I think it would be plutonium. In other words, the recycling of weapons,
Mhm.
materials into
Mhm.
power reactors has already been going on.
Is it?
Oh, yeah, I think so.
Oh, even in Japan.
This area,
Yeah, I believe so.
Yeah.
One of the reactors.
Yeah, yeah,
Well, that's good.
yeah.
It's
Um,
unfortunate.
Well, good thing.
Well, there's a guy who came to one of these talks named Peter something, whose name I can't quite remember, but I would recognize it if I heard it, maybe a man your age, who is really promoting the idea of somehow being able to get rid of all the waste products that we have by reusing them in this way.
Yes.
He's got papers. He gave me a copy of a paper, which of course I couldn't read, but it was an argument that in the long run, that's how we're going to dispose of all these horrible things.
Yeah, well, as we've said several times, plutonium can be used in a reactor to produce energy. You don't have to store it in the ground. It's a bad idea for many reasons. First of all, it's very long-lived. There's other things besides plutonium. There's other what they call transuranic elements, heavy elements, which have long half-lives, but I don't think there is much of them as there is plutonium. Would you agree?
I'd like to make a comment about
Yeah.
that, because you've made a very good point that plutonium can be put as a starter fuel. I mean, to start the thorium
Certainly.
reactor, you don't initially have any U-233.
Yeah.
So you can add on the first round, until you get some U-233,
Yeah.
you can add the plutonium.
Yeah, that's what the Indians are
Now,
proposing.
the nice thing about that is that the plutonium then gets used up. By the way, it never all gets used up, but
No.
some of it gets used up, so you reduce the number of plutonium. But it was only about 10 years ago we had this MOX fuel controversy. MOX mean mixed oxide fuels,
Yeah.
where everybody was talking about mixing plutonium oxide with uranium oxide to get rid of the fuel, to get rid of the plutonium, for example, in light water reactors. And
Yeah.
this, in fact, was done. It was
Yeah.
done in Russia, it was done in the United States. But I pointed out, and I don't know if it's in print anywhere, but I've pointed it out many times, that to do this is the minute you get rid of the plutonium in the minimal way, because you're recreating plutonium in the uranium rods
Yeah.
that already contain plutonium. So you're getting rid of some and then building it up again.
Yeah.
So the point I
And
made
you
is,
get more than you
Yes.
lose, or
it depends. I think you use more than you gain,
yeah.
but it's a very slow rate of
Slow
decline.
process, yeah.
But so I made the point: why not mix the plutonium with something that doesn't contain uranium?
Yeah.
For instance, like zinc oxide or something
Mhm.
that doesn't have any important
Yeah.
nuclear properties. But this idea of doing it with thorium is just as good.
Yeah.
But this maximizes the rate at which you get rid of the plutonium.
Like
The
using
MOX
thorium.
fuels, which people were writing papers about 10 years ago, minimize the rate of
Yeah. Yeah.
net usage of the plutonium.
So this is an argument for using thorium.
It's an argument for using thorium.
Yeah, great. Okay, so I think I have one or two more slides. Oh yeah, one idea is in the States, the thorium liquid reactors make medical isotopes. I think that actually one of the Canadian reactors at Chalk River does that. Am I right? Do you know? I seem to read that on the web lately, the last couple of days.
Nordium. Nordium, isn't it? They privatized the isotope.
Oh, they probably privatized it, yeah, but,
They were in the process of refurbishing it.
I don't think what they use is a liquid fluorine one, but it's sort of Cantab type, but I think they use thorium. Because it's on the list of 14 thorium reactors in the world. It's still, one of them's still working. They can make medical isotopes at a company called FLY, which is short for fluorine, lithium, and beryllium, which is what they use in these liquid reactors. They plan to finance thorium power and thorium plants to produce electricity by selling medical isotopes. They think they can make $500 million a year, $500 million a year, and then finance the power plants. Another company called TerraPower, along these lines, is chaired by Bill Gates, who, as the author says, he can finance, he can build 2 nuclear plants and still have money left over to eradicate malaria. That was supposed to be a joke, I suppose. And also, there's a company in South Africa that's trying to build thorium reactors, and they're supposed to be much cheaper than whatever they have now. Apparently, power in South Africa is incredibly expensive, and the Japanese scientists and industrialists are planning along these lines. Now, the conclusion of the book I don't necessarily agree with, but it's an interesting point. He says the Romans, towards the end of their empire, lacked cheap fuel, which in their case consisted of grain. They didn't have any other kind of fuel except grain to power human and animal energy, muscles. Although there was a Greek scientist or engineer who designed a steam engine, at least one. The Romans, whether they knew about it, I don't know, but we seem to know about it, and they neglected steam power. They didn't carry on with it. And he says we must not make the same mistake with respect to thorium, because that's because, by the way, the Indians say if we don't use thorium, we run out of uranium, we're doomed, because continuing to use fossil fuels will cause a runaway heating effect, as most people know. Most people with any sense know it anyway. So he says we must not make the same mistake with respect to thorium that the Romans did with steam. And by the way, as an aside, as a semi-joke, it may be just as well that they didn't invent the steam or pursue the steam engine, or we would have had greenhouse effect 1,500 years ago. Now, as I think I said earlier, wind is not, and perhaps to some extent solar, is not that much more expensive than, say, thorium, but it could be a problem for, the extra expense could be a problem for poorer people in our own countries, developed countries, or poor countries that are altogether poor.